Hello everyone, myself Dr. Sunny Kumar. I am an assistant professor in Department of Chemical Engineering, PKG College of Engineering and Technology, Panipat. Today I will teach unit process. This is my lecture 9. So these are some schematics which we have discussed in the previous lecture. So the previous lectures we have discussed about what are the factors which are controlling the alkylations, effect of alkylation, technical alkylation, alkyl aryl detergents, alkylate for the petroleum industries. So these things we have discussed in the last lecture, and we have discussed so this is a reaction which is we are prepared the detergent which is dodacyl benzene, and dodacine propyl benzene is your reactant and the benzene is your reactants. So these two component at 115 degree Fahrenheit in the presence of aluminum chloride we will get this dodacyl benzene. So this thing we have synthesized in the last lecture, and other components also which are the alkylate for the petroleum industries, and what are the uses for the catalyst for different catalysts we have also seen. So this thing we have discussed in the previous lecture, and this is your flow diagram for the detergent. You are preparing a detergent which is alkyl aryl sulfonates, and the the common reactants are dodacine and benzene. When both are reacting, we are sending to this storage contractor, and then these are the three fractionator we are using. The first one is benzene fractionator, second one is intermediate fractionator, third one is dodacyl benzene fractionator. These three are fractionator we are using. These after the purifying this we will set to this storage tank where we will get this dodacyl benzene storage, and we are again treated with this sulfuric acid and this in the sulfonator container, and this is a spent acid settler where the spent acid we are getting from the bottom, and from the bottom from the side of the bottom we are getting the dodacyl benzene sulfate sulfonic acid, which is directly we will send to the neutralizer where we will treat with the sodium hydroxide solution, and we will getting sodium dodacyl benzene sulfonate slurry. So this is we are getting, and after that we are directly sending to the crusher where this is mixing there, and then we will directly sending to this spray dryer. In spray dryer we are drying our this slurry with the help of combustion gases which are producing by the furnace, and this treated with the treated this solution and sprayed, and then we will get the dry detergent for the packing purpose. So this is a flow sheet for the alkyl aryl sulfonates we are producing for the detergent purpose. So this is a very simple diagram where we are using the aluminum chloride as a catalyst. So this is the thing. After that so in today lecture we will discuss about alkyl bonds to oxygen, where we will discuss acetophenetidine, this anisole, cellulosive, carbitol, ethyl cellulose, sodium carboxy methyl cellulose, codeine, vanillin, and the alkyl bonds to trivalent nitrogen, which have the other compounds like diethylamines. So these are the different components which are producing which are common for the trivalent nitrogen and the alkyl bonds to the oxygen. So these things we will discuss today. So the first we will discuss cumin. So cumin has a long been important constituent of aviation and high quality motor fuels. However, it has become an important step in the manufacturing of phenol and acetone by oxidation. So this is a simple reaction. So this is a propylene, benzene, and this is a hydrophosphoric acid H3PO4. So you are getting C3H7 isopropyl benzene plus C2H7 and C6 polyisopropyl benzene. So you will get this thing. So how to prepare preparation of this? So the preparation of cumin or isopropyl benzene is frequently carried out at about 25 °F and using phosphoric acid catalyst, and the reaction is exothermic and also produce polyalkylated benzene even with high ratio 5:1 for benzene to propylene. So the benzene to propylene ratio is 5:1, and this is the exothermic reaction. So the polyalkylated benzene can be used to an extent limited by their boiling points in motor fluids, or they can be dealkylated and realkylated. So the another components we can also produce the ethyl benzene. The ethyl benzene has been made in very large quantity in recent years as a step in manufacture of styrene for GR as synthetic rubber and for plastics. The reaction involved are essentially, so this is your reaction. So this is a benzene and this is C2H4 ethylene, so that you will get it C4H3 C2H4. So this is a exothermic reaction where minus 48,700 BTU per lb moles at 95 degrees centigrade. This is your enthalpy. So the preparation gaseous ethylene is passed into the liquid benzene. So this is ethylene gas we are passing to the liquid benzene in the presence of metal chloride catalyst such as aluminum chloride at moderate temperature 40 to 100 degrees centigrade. So the reaction is promoted by hydrogen chloride. So this reaction is promoted by the hydrogen chloride. So this is the flow sheet for the ethylene benzene which we are producing using ethylene and the benzene. So this is ethylene and ethyl chloride here. So this is alkylator, and from the top you are getting the off gases, and from the bottom you are getting the liquid charge, and this is reaction mixture separator, and here it is a water and caustic soda, and then you are sending for this so this is in this column here, and from here benzene you are sending to this benzene drying column here, and from the top you are getting the benzene, and here you are drying this dry benzene from the bottom, and you can directly liquid recharge here in alkylator, then reaction mixture and separator. After that you are sending this in this column, and this in this reactor the atmosphere is around 10 atmosphere here, and this is cool condenser is there, the cooling by the cooling water we are cool the system here, and then after that again ethylene benzene column, this is ethylene benzene column is there, where from the top you are getting the product ethyl benzene, and from the bottom you are getting again by the treating again column, so you are getting this polyethylene benzene to dealkylations, and from the here you are getting the bottom you are getting the residue, and from the top your polyethylene benzene to alkylation you are getting, and this is a PEB column, polyethylene benzene column. So this type this is the way you can produce this is a continuous flow diagram for ethyl benzene, where the two reactants are the ethylene and the benzene are the two components, and you are using the catalyst. The catalyst the metal chloride catalyst generally used, which is aluminum chloride, and 40 to 100 degree centigrade is the temperature of the reaction, and reaction is promoted by hydrogen chloride. So this is your flow diagram. You can easily see how to synthesize this ethyl benzene. A continuous process for ethylene benzene we have shown in the previous figure. You can cite as a 14.8. So anhydrous conditions must prevail, hence the 99% purity benzene is pumped through an azeotropic drying column, which benzene with less than 30 ppm water is withdrawn. The benzene is mixed with recirculated catalyst complex and fresh catalyst, anhydrous aluminum chloride. So the hydrogen chloride, which serves as promoter, is furnished indirectly from the ethyl chloride mixed with the ethylene, and 90 to 95 mole percent per purity you are using the ethylene. So the ethyl catalyst complex consisting of heavy organics and solids anhydrous aluminum chloride is separated as we have seen in figure 14.8, and the recycled after mixing with needed fresh aluminum chloride. That the fresh aluminum chloride, the catalyst, enhanced the production of ethylene benzene. Okay, so an approximate composition is, so aluminum chloride combined with hydrocarbons, which is 26%, and aluminum chloride free is 1%, and the high molecular weight hydrocarbons are 25%, and the benzene and ethyl benzene is 46%. So this is a composition of the different components. In the alkylation, the benzene is converted to ethyl and polyethyl benzene, which is we have seen in 14.7 figure at 200 Fahrenheit, and a pressure is slightly above atmospheric. Okay, so as the reaction is exothermic, heat must be removed by the evaporation or cooling. So the crude alkylate is separated from the catalyst complex, cooled and washed with water and then with caustic soda solution. So the crude product contains 40 to 45% benzene and 15 to 20% polyethyl benzene, and a small amount of tar, the rest being ethyl benzene. So the separation is effected as shown in figure 14.8 by a train of conventional columns. So you will see here. So from the top you are getting the polyethylene benzene. Actually there is a two components which are generally we produce. The first one is by reacting, when you will react ethylene and benzene, at a specific temperature and using a specific catalyst. So you are getting the from the first you will get the ethylene benzene, and the another component you are getting polyethylene benzene. So by these columns you can easily separate the ethylene benzene and polyethylene benzene. Okay, a catalyst aluminum chloride. As the reaction this reaction is exothermic, heat must be removed by the evaporation or cooling. The crude alkyne is separated from the catalyst complex and cool washed with water and then with caustic soda solution. This crude product have 40-45 benzene, 15 to 20% polyethylene benzene, and a small amount of tar, rest being ethylene benzene. The separation is effected as shown we have in the conventional columns. So with the third one operated head pressure of about 50 mmHg absolute. The furnishing an overhead of the polyethyl benzene which is charged to the realkylator using aluminum chloride and excess benzene at higher temperature and different catalyst ratio. So the ethylene benzene and dimethyl benzene we are getting results. Okay, so this is you have produced ethyl benzene. Okay. So now we will produce hexyl resorcinol. So this is a formula for this one. So the normal hexyl resorcinol has been found to, this is a benzene group and this is which is attached the OH and OH from the these different position, and this is a long chain molecules is available, has been found to possess marked germicides property with a phenol coefficient of over 50. So it is relatively non-toxic when administered by mouth and is partially exerted by the excreted by the kidneys. So this is also a very medicinal components which is used for the pharmaceutical purpose. Industry generally they are using this one. So a great number of acyl and alkyl resorcinols have been studied as regard their germicidal actions. The normal alkyl resorcinol particularly have been found to be a very pronounced increase being observed in the bactericidal power shown by these compounds up to normal hexyl resorcinol. This action then decreases as the length of the chain increase because of the diminishing solubility of alkyl resorcinol. So the 14 point the figure corresponding figure we will show in next slide. So the relationship between the atomic weight of the alkylate chain and the phenol coefficient ratio of antibacterial power measured against Abarthella thyposa relative to that of phenol under the same condition. Similar experiment with different strain of Staphylococcus aureus gave results shown in table 14.8 that we will show in the next slide, I think. Okay, so the preparation according to the various patent pertaining to the manufacture of hexyl resorcinol and resorcinol and the caproic acid are heated with a condensing agent such as zinc chloride, whereby the intermediate ketone derived is formed. So this is a purified by vacuum distillation. So this is a reaction where Z and chloride are using as a catalyst, and these are the two-step process you are getting. and by reduction with zinc amalgam and hydrochloric acid, impure hexyl phenol results, which can be purified by vacuum distillations. Okay. Just 1 minute, I will show you um, the, um, the diagram which is used for the that purpose. 14.8 table. I am showing just 1 minute. Within a 1 minute, I am showing you. Okay. For a 1 minute, I am showing this one, the 14.8 diagram, which is this is a diagram. So we are just showing table 14.8. So this is your 14.8 table, which is showing the coefficient of the normal resortional with different strain of Staphylococcus aureus. So these are the different alkyl derivatives: ethyl, propyl, butyl, amyl, hexyl, heptyl, octyl, and nonyl. And these are the different phenol coefficients, and this is on the strain 1, strain 2, and this is strain 3, and this is 1.5 ethyl, and by strain 2 1.5 and 1.5 in strain 3, and propyl for 3.9, 3.7 and 3.7 for strain 3. So and the butyl 10.7, 10 and 10.2, and for the amyl, which is 30.2, 30.2 and 30.6, and for the hexyl it is 97, 98 and 98, and for heptyl it is 295, 280, 280. Octyl it is 690, 680, 5. Nonyl 1000, 980, 1000. So these are the different phenyl coefficients for at 25 degrees C, and these are different alkyl derivatives for the different alkyl derivatives. So this is your 14.8 figure which we have discussed, and another figure which is 14.9 which is used for this hexyl resorcinol, which is this one. This is the figure for 14.9. This is the bacterial activity of the alkyl resorcinol. The curve is obtained by the plotting phenol coefficient. This is the phenol coefficient, and n ordinates against to sum of the atomic weight of the atomic in the alkyl chain as apacious. So this is the two things we are, and these are n-butyl and amyl. So these are the different points which is showing here, and that is tabulated in the 14.8 table. You are seeing this. So this is the thing according to the atomic weight. Okay, so that figure 14.9 shows the relation between the atomic weight of the alkyl chain and the phenol coefficient, and the ratio of antibacterial power measured against the Abarthia typhus are relative to the that of phenol under the same conditions. Okay. So this is we have already discussed. Now we will discuss about the alkyl bound to oxygen. So this is a there are actually this thing we have already discussed, how the alkyl bound with to the oxygen, what are the different compounds. So this anisole, cellosive, carbitol, ethyl cellulose, sodium carboxyl, methyl cellulose, and codeine and vanillin. So these are the different components which are in which the alkyl bonds to the oxygen. Okay, so so the first one, the acetophenetidine. So acetophenetidine is an important allergic and antipyretic that has be attained widespread use in medicine, and the principal series of reaction for its preparation are given below. So this is the reaction. Okay, see reaction you can see properly here. If you will expand it, so this is a NH2COCH2 here, and this is the reaction C2H4 OK K2S4. So these NO2 and NH4 again. So these are the different chain reaction is there, 1 2 3 4 5 6. There is 6 step reaction. So this is another reaction. This is reaction 2. So where we this phenol is treated with sodium hydroxide and C2H5Cl, and then again NaCl produce, and then again both are reacting, this one and this compound we will react, and then you will get the combination of this, and then reduction is happening. So this only compound is there. So this is acetophenol. So these are the acetophenol is an the principal series of reaction of its preparation are given, we have shown you, and the one involving the nitration of chlorobenzene is of most valuable technically. That these reactions are intertwined with the preparation of other products. Examples: orthonitration, product of either chlorobenzene or of phenol, is methylated to give orthonitroanisole, which is made into guaiacol or dianisodine. So next compound is anisole. So anisole is used directly in perfumery and is an intermediate for further synthesis, and it is prepared by action of methyl chloride or dimethyl sulfate on phenol. When dimethyl sulfate is employed, both of its methyl group can be made to react, yielding about 72 to 75% of theory of the anisole. When only one of the methyl group is caused to react, the higher yield being 85 to 95 percent of the theory, but it is usually more economical to use both of the available methyl group. And if you will see this reaction, we will see this reaction. This is outline of reactions. So C5 this ONA and S2CO and which is compounded with SO2. So this is the compound you will get, and plus sodium oxide and S2CO SO3. So this thing you will get it. And another reaction is this one, where sodium bisulfate is getting. Further, this is treated with this one, and again this with the CS2Cl you are getting C2H5OCaC plus NaCl. So this is the proper reaction of anisole. Okay, so this is available methyl groups are you are seeing here. Okay, again we will discuss this is the another topic, which is alkyl bound to trivalent nitrogen. If you want to read the this full detail of the anisole, you can read in the textbook, which we have already described in the lecture 1. Okay, so alkyl bound to this trivalent nitrogen. So dimethylamine is a major component, which is C2H5 2NH. Okay, so dimethylamine finds extensive use in the preparation of wetting and dispersing agent, and then and enter into many syntheses. Through its employment, the alkyl groups are introduced into procane, its preparation from ethanol and ammonia by ammonolysis. The Schweitzer also described the synthesis from ethyl chloride and ammonia. Ethyl chloride and ammonia. So this is your simple reaction, which is the ethyl chloride plus ammonia. So you will get ammonium chloride, and this is diethylamine. So this is a diethylamine, NaC2H5 twice. Okay, so this is dimethylamine compounds we are getting. So next is alkyl bound to the trivalent nitrogen. So we will discuss about the dimethylaniline is widely used as an intermediate in the manufacturing of dyes, rubber, accelerator, explosives, and some medical products. So this is a formula for dimethylaniline. So this is such important dyes as oramine, malachite green, methyl violet, crystal violet, and methylene blue are derived from dimethylaniline. These compounds also find application in the preparation of quaternary alkylating compounds such as described under codeine. The explosive tetraethyl, which is trinitro phenyl methyl nitroamine, is manufactured by the nitration of dimethylaniline. The present technical preparation of dimethylaniline depends upon heating aniline, excess methanol, and an acid in an autoclave. So this is a C2H5NH2 plus CH2OH methanol. So dimethylaniline, and so this is you are getting here in the presence of as sodium hydroxide. So it is H2SO form. Sorry. Okay, H2SO sulfuric acid, so plus H2O you are producing. So this is simple reaction which is we are getting. The further part of this dimethylaniline we will read in the next lecture. Okay, so in today lecture we have discussed about alkyl bound to oxygen, which is acetophenetidine. We have read an anisole, cellulosive, carbitol, ethyl cellulose, and sodium carboxy methyl cellulosive, codeine, vanillin. So these are the compounds which are alkyl bound to the oxygen. So few compounds we have discussed today, and the another is alkyl bonds to the trivalent nitrogen, which is diethylamine, and the another one is dimethylaniline. So these compounds we have discussed today. So and instead of this we have also discussed ethyl benzene and cumene. So these two compounds we have also discussed, and related this how ethyl benzene flow diagram is we have described. So in the continuous flow diagram for ethyl benzene we have also prepared, where the main reactants are ethylene and benzene, where reaction is mixture in separators, different separators, and for a specific catalyst and its specific temperature and conditions. So these are the two different columns, 2-3 different columns are there, and you are producing the products is ethyl benzene, and you are also getting the polyethylene benzenes, but you have to separate it by this ethyl benzene column. From the bottom you are getting polyethylene benzene, and from the top you are getting the ethyl benzene. So the purification you can also do, and what are the different ratio you can also see, we have described, and we have given the different conditions. So this is the continuous flow diagram for ethylene benzene. So this thing we have discussed, and the aluminum chloride is a main catalyst for this, and the hydrogen chloride is also used during this reaction. So and this hexyl resorcinol we have also discussed. So these are the compounds, and related to what are the different normal resorcinols with different strain of the Staphylococcus aureus we have also discussed. So this thing we have discussed in today lecture, and so in the next lecture we will discuss about the alkyl bonds to the trivalent nitrogen. So this is dimethyl already discussed we have, but this dimethyl aniline we have some part we have discussed, and remaining part we will discuss in next lecture. And this alkyl bonds to lead and sulfur we will discuss, and tetra ethyl lead we will discuss, lauryl mercaptan compound we will discuss, that is very important compound which is used for detecting the leakage in a gas cylinder. So this is also very good component. So these are the things we will discuss in the next lecture. So thank you very much. So if you have any doubt related to this lecture, and whatever the topic we have discussed, if you have any doubt, so you can email me. My email ID is chemicalsuniraj@gmail.com, and my website is this is the site .google.com site and /nature science naturesuniraj1 /. So this is my website, so you can directly contact if you want to further read. So this is the thing. So thank you very much again.